Hello, physics students. This is the last section of Chapter 2 lecture. So where we left off in class was on the concept of free fall or projectile motion. Free fall is where the object in question is only under the influence of gravity, nothing else. No other forces are happening. So gravity, as we'll learn later in later chapters, is a force. And a force is what causes an acceleration on an object. So if an object is, nothing else is happening, there is an acceleration due to gravity, and it is straight toward the center of the earth. The acceleration vector points straight to the center of the earth. And for all objects near the surface of the earth, it is always going to cause an acceleration that is 9.8 meters per second squared, pointing toward the center of the earth. Remember we watched that video. It's a really good video. I would encourage you to watch it if you hadn't already, showing a bowling ball and a feather in that chamber where all the air can be removed, so it's creating a vacuum, fall to the ground at the exact same speed. Alright. So here's a motion diagram of an object that is falling straight down. So what is happening to the velocity? The velocity vector points downward, and it is longer as time goes on. It's gaining velocity. It's gaining more and more negative velocity as time passes. So this would be a good example of a velocity graph of an object that is just dropped, just released. So the velocity vector has a slope. It's a changing velocity. And that slope is the change in velocity, which in this case is a constant of negative 9.8. We call that 9.8 g. So g is 9.8, and so the acceleration due to gravity is negative g, or negative 9.8. Other planets have different values of g, and this is also for objects that are of relatively small size compared to the Earth. So like a planet, another planet, it would be something different going on there that we would have to talk about later, because it would have its own gravity that would be happening also. Alright, quick check 2.18. A ball is tossed straight up in the air. At its very highest point, the ball's instantaneous acceleration, a sub y, is what? Positive, negative, or zero. At the very highest point, the acceleration is negative. It is negative 9.8. It's negative 9.8 the whole time. Whether it's still going up, if you toss it up, whether it's still going up, whether it's at its very highest point, or whether it's on its way down, the acceleration is constantly negative 9.8. Now at that highest point, the velocity is zero. The position, if you consider the ground to be the origin, the position is positive, but the acceleration constantly in this case is negative. Alright. Here is an example, 2.13. This is kind of a famous example from my first physics class. The guys in that class loved this example for some reason. The springbok, an antelope found in Africa, gets its name from its remarkable jumping ability. In fact, they said they should make a tennis shoe and call it the springbok. When startled, a springbok will leap straight up into the air, a maneuver called a pronk. So, yeah, springbok goes into a crouch to perform a pronk. It then extends its legs forcefully, accelerating at 35 meters per second squared. That's the acceleration for 0.7 meters as its legs straighten. So the 0.7 meters is the length, the distance that those legs extend, creating that acceleration during that extension. Legs fully extended, it leaves the ground and rises into the air. How high does it go? Alright, before we get into this, I do want to show you a little video of a springbok. I hope that you can see this video well. I hope so.
Springbok have been roaming this desert for many months, searching for one of these rare and highly localized downpours. The grass is sprouting. And that is worth celebrating.
That is a pronk. We get ready for some more impressive ones.
If you're a springbok, that means pronking.
If I could jump like that, I would do it too. That is amazing. It's just like a little miniature flight. Look at that. That's crazy. That is so cool. So they don't just prompt when they're startled, they prompt when they're attitude. And I think springbok would be a great name for a sneaker.
You still don't know exactly why they do this. The simplest answer is that they're dancing for joy.
That's a better question. Okay. I'm just going to write down some things that I remember from the problem. I was told that the acceleration from the jump is 35 meters per second squared over a distance of 0.7 meters. So what happens, I'm just going to draw a little motion diagram. Let's say this is the center of mass of the springbok. It's accelerating upward, so it maybe like that, then like that, and let's say there's where it leaves the ground. All right, leaves ground. So after that, it's going to have a negative acceleration. So it's still going to be going up, but not as much. And let's say this is its highest point. So here, throughout here, we have A is 35. Throughout here, we have A is negative 9.8 after it leaves the ground. So, I think we need to do this in two phases. Phase 1. Alright. Phase 1 is when the springbok is extending those legs and accelerating upward. So A equals 35. So then V, F would equal the antiderivative of this, which is 35t, plus v naught, which we'll say is 0. You know, at the bottom of his crouch, his velocity is 0. Alright, so then yf for phase 1 will be 35t squared over 2. So that was that 17.5 t squared plus the initial y value, which we'll just call that 0. Alright, phase 2, A is negative 9.8. So VF is equal to negative 9.8 t plus VI plus VI. And this VI, by the way, is going to be the VF of phase 1. Right? Because at the end of phase 1, he's going a velocity that then becomes the initial velocity of phase 2. So YF in phase 2 is going to be negative 4.9 t squared. So it's negative 9.8 t squared over 2, which is negative 4.9 t squared, plus VIT. And again, that is also the same as that other VI, plus Y initial. And that Y initial is like the height of this when he leaves the ground, but I think I can still call that 0 because I want to know how high he gets. So this is still him on the ground, so I'm still going to call that 0. So I'm just going to erase that. Okay. All right. So then, this is a fairly involved problem. I mean, this is not an easy, simple problem. It's a real, true, sure enough physics problem. All right. I think what I'll do is think about what do I know? Do I know any of these values here? What I'm ultimately trying to find is this. That's what I ultimately am being asked to find. I know that this is that final height, is that final value for phase 1. That's how far his legs extend. So 0.7 is that YF. And that will allow me to find T. Once I find that T, I can plug that in here, and I can find that VF. So let me do a little bit of calculator work. All right, after dividing by 17.5 and taking the square root, I get T is equal to 0.2. So 0.2 seconds is how that happened. So I've got that. I'm going to plug it in there. All right, not there, sorry. I'm going to plug it in there and to get my velocity there. So 35 times 0.2 is 7. So this VF equals 35 times 0.2, which is 7. All right, now let me go back over to the phase 2. All right, this VI is 7. And this VF, do I know that? Yes, I do. Because that final velocity at the highest point is what? At the highest point, that velocity is 0. All right, so we're in business now. 0 equals negative 9.8 t plus 7. All right, I can solve for t now. I can subtract 7 and divide by 9.8. 7 divided by 9.8. 0.714 is t. And then this can go into t here and here. And that's all I'm doing, because I've got all these variables. The only one I'm missing is y sub f, and that's going to be determined. So y sub f equals negative 4.9 times 0.714 squared plus 7 times 0.714. And y sub f then will equal you got to type this in the calculator. $2.49999. So basically 2.5 meters. So that springbok jumps 2.5 meters in the air. That's pretty high. That's like 8 feet. Wow. That's a pretty good vertical jump right there. All right. Let's go back to the PowerPoint. Feel free to read this explanation. And feel free to read this explanation. And this one. But notice that they do get the answer to be 2.5. And this one. Alright. Motion on an inclined plane. Figure A shows the motion diagram of an object sliding down a straight, frictionless inclined plane. Figure B shows the free fall acceleration the object would have if the incline suddenly vanished. This vector can be broken into two pieces. This symbol means a parallel. This symbol means a perpendicular. They stand for these two components. You have So the true acceleration, the acceleration due to gravity, always points toward the center of the earth right here. But then that, because now this object is moving down this incline, is not moving along this line, this acceleration vector is now broken up into two separate components. One component is going to be the component parallel to the ramp, and the other one is going to be the component perpendicular to the ramp. Alright, the surface somehow blocks a perpendicular, so the one-dimensional acceleration along the incline is going to be determined by trigonometry, by this right triangle formed right here. Alright, let me blow that up. Alright, so you can see in this triangle now, here is the right angle. Okay. Alright, the theta for the incline that the incline makes with the ground. If we think about that, you know, if we can put that same angle somewhere on this triangle, it is going to go here. Alright, that's the same angle. And therefore, this is the opposite. This is the hypotenuse. Therefore, sine of theta equals the opposite over the hypotenuse, which is a parallel, over a free fall. And then if we want to know a parallel, then it will just be multiplying by a free fall on both sides. So a free fall times sine of theta equals the parallel component of that acceleration now. And that is what is said right here. It's g, which is the acceleration of free fall, times the sine of theta. That is a sub s. That is the acceleration along the surface. The acceleration parallel to the surface. The correct sign depends on the direction the ramp is tilted. Alright, quick check 2.19. The ball rolls up the ramp, then back down. Which is the correct acceleration graph? Okay. Which way, so if we consider this to be the positive direction, consider up the ramp to be positive, which way does the acceleration point? The acceleration is going to point down the ramp. It's going to oppose the velocity up the ramp here. So acceleration is negative then. It's a negative value, and it's a constant negative value. As the ball goes up, acceleration constantly is doing the same thing that it continues to do, whether the ball is rolling up or whether the ball is rolling down. It's a constant negative acceleration. Choice D is the correct choice. Alright. Thinking graphically. Consider the problem of a hard, smooth ball rolling along a smooth track made up of several straight segments connected together. Your task is to analyze the ball's motion graphically. There are a small number of rules to follow. Assume that the ball passes smoothly from one segment of the track to the next with no abrupt change of speed and without ever leaving the track. The graphs have no numbers, but they should show the correct relationships. For example, the position graph should be steeper in regions of higher speed. The position S is the position measured along the track. Similarly, V sub S and A sub S are the velocity and acceleration parallel to the track. So here's an example of that. Considering this particular track, draw the position, velocity, and acceleration graphs for the ball on the smooth track. Alright, I'm going to try to do this in both the horizontal and vertical dimensions. So if I'm doing the horizontal dimension, I'm saying X is its horizontal position, and I'm going to let its initial horizontal position be 0. Alright, it is pushed with some velocity, some positive velocity greater than 0. So that means that its horizontal position is changing. It's going away from the horizontal. If this is the origin, this is the horizontal origin, it's moving away from that in the positive direction. And it's flat, so it's going to be doing that at a steady rate. But then as it gets to here, it's going to accelerate because of gravity. It's going to be accelerating in this direction and in this direction at the same time, because it's going, this vector is going to accelerate both that way and that way. So horizontally it is accelerating. So it's a linear situation there. But once it hits this point right here, it's going to be accelerating. So I have to show that with a curve. It's not constantly a constant rate of change anymore. It's not. Remember, the slope of position is velocity. Well, it's no longer a constant velocity. It's an increasing velocity. So I have to show that with a curve until it gets to here. And at that point, it's flat again. And so it's a constant, but it has the same final velocity as it did here. So that's what it should look like. It's got a greater velocity after it goes down the ramp than it did when it first started. So that has a steeper slope there. All right, if I do the Y position, all right, now I'm looking at the vertical position. So let's call All right, let's call the ground the origin. This is the origin now, the ground. So then it starts with an initial position vertically of something greater than 0. And for a little while, that vertical position does not change. It's the same vertical distance away from the origin as it was. Then it accelerates down the ramp, so it's going to be accelerating that way. So its velocity is going to be negative, so it's going to be taking it toward the origin increasingly. So not at a constant, but with a curve until it reaches all the way down here. So it reaches 0, and then it stays at 0. So that would be that graph. All right. What about the velocity in the horizontal direction? All right, the velocity over this period is a constant positive velocity. Right, I'm seeing that as the slope here. Then over this curved portion of the graph, it's going to be the velocity is going to be increasing linearly. Right, the derivative of a parabola is a linear situation. And then here, it's again a constant slope, so it's a constant velocity. But it's a higher constant velocity than it was at the beginning. All right, vertically, the vertical velocity graph would be, it starts out with a slope of 0, so a vertical velocity of 0. It's not going toward, it's not moving vertically at all. It's moving horizontally, but it's not moving vertically at all, so it has no vertical velocity until it gets to here. Then it begins to increase negatively in its vertical velocity. All right, until it gets to here. When it gets to here, it's supposed to be a linear situation there. When it gets there, it's just 0 again. So it's kind of a disjoint right there. And that happens anytime you have like a corner. All right, what about acceleration? Acceleration, horizontal acceleration. Acceleration is the slope of velocity. So at first, the horizontal acceleration is 0 until it gets to that first point right there. Then it is accelerating horizontally. So it has a positive acceleration. Some positive acceleration, and that's just the slope of this velocity right here, that section of velocity, until it gets to there, and then it no longer has a horizontal acceleration. The horizontal acceleration is just 0, which is the slope of this section. So that would be the graph of horizontal acceleration, and the graph of vertical acceleration will be 0, and then some until it gets to there, and then some some constant negative value for acceleration, and then 0 acceleration again there. Okay, and here is that explanation from the example itself. You can feel free to read that. They're only giving the horizontal part of this, by the way. We did the horizontal and the vertical. So we did a little bit more thorough explanation. All right, another example. Figure 2.34 shows a set of motion graphs for a ball moving on a track. Draw a picture of the track and describe the ball's initial condition. Alright, each segment of the track is straight, but the segments may be tilted. So this time we're given the position, velocity, and acceleration graphs, and we're told to sketch the track. Before it gave us the track and we had to sketch the graphs, but now we're given the graphs and we're supposed to sketch the track that would be associated with those graphs. Alright, so first of all, this ball has some initial velocity that is making it go away from its horizontal origin at a steady rate. So a constant positive velocity. So let's just say it's going flat. Here, so the first part of my track is flat till it gets to there. Let's say that represents this spot right here. Then it is what is the slope of this thing doing now? It's getting less and less. So it is negatively accelerated. It has a negative acceleration horizontally. How can we do that? Well, it certainly wouldn't be a downhill track. It would be an uphill track. That would make the acceleration point this way, right? The acceleration would be, as far as horizontal is concerned, would be pointing that way. And it's going to, so at right here is where it actually begins to roll back down toward its horizontal origin. So let's just say that happens right here. So it's going to go up the track, but then it's going to go back down the track. And yeah, so then when it gets to here, it looks like it flattens back out. But it hasn't yet reached that horizontal origin when it flattens back out. So when it comes back down the hill, there must be some kind of a separate ramp or a separate switch that makes it go flat before it gets back to where it was horizontally. So as it goes back down, then it comes here. So that produces this linear situation where it is going back toward its horizontal origin at a constant rate. And in fact, it goes past, so if it started here, it goes past its horizontal origin into going to the left of its horizontal origin, so it needs to come on this way. And the ball ends up somewhere over here. Let's see if that fits the velocity. Starts out with a positive velocity, then that positive velocity decreases until this is where it would hit its the point where it would turn around and go back toward its horizontal velocity, its horizontal origin, so somewhere in here. And then it has a negative. After that, it has a negative velocity, which means it's moving back toward its horizontal origin. And then it has a constant negative velocity, which is when it hits actually this higher, the switch. It hits the switch and it gets on this part of the track that's flat. Let's think about that acceleration. It starts out with a zero acceleration, so that's when it's on this flat part going this way. Then it has a negative constant acceleration. That's when it gets up on this part of the track. And it continues to have that negative acceleration until it gets back on this other flat part of the track. So, I'm sorry, it started out that way, then gets up on the track, then comes back down and goes that way. Okay. That was very confusing. If you were confused by that, don't worry. You would be in good company with a lot of people. But that is also the explanation of this that you can read as well from the publisher. Advanced topic, instantaneous acceleration. Figure A shows a realistic velocity versus time graph for a car leaving a stop sign. The graph is not a straight line, so this is not motion with a constant acceleration. So this velocity is not straight. It's not linear. Right? The slope of this velocity is changing, which means that it is not a constant acceleration. Our velocity would have to be linear in order to have a constant slope, which would be the constant acceleration that we would be looking at. That's not the case here. So figure B shows the car's acceleration graph. The car speeds up from rest until it reaches a steady cruising speed. The slope of the velocity graph is the value of the acceleration graph. So this is a very high slope, right? Which means the acceleration has a very high value. But the slope of this is getting less and less and less. It's flattening out, right? Which means the value of acceleration is getting closer and closer to zero. Every slope here is associated with the value here. All right. So if this is a slope of 12, this would start out at a value of 12. If this is a slope of 6, this would be down at a value of 6. If this is a slope of 1, this would be down at a value, a height of 1. The instantaneous acceleration, a sub s, is the slope of the line that is tangent to the velocity versus time curve at time t. In other words, a sub s equals dv sub s over dt, which is the slope of the velocity versus time graph at time t, also known as the derivative of the velocity versus time graph. We're almost to the end. Suppose we know an object's velocity to be vi sub s at an initial time ti. We also know the acceleration as a function of time between ti and some later time tf. Even if the acceleration is not constant, we can divide the motion into n steps of length delta t in which it is approximately constant. In the limit delta t approaching 0, we can compute the final velocity as this. So it's just saying that the integral of acceleration, which involves the antiderivative of acceleration, is going to be what gives you velocity. That's something we already knew anyway. Then the graphical interpretation of that is also that the area under the acceleration curve gives you velocity. So here we go. Example 2.17. This figure shows the acceleration graph for a particle with an initial velocity of 10 meters per second. What is the particle's velocity at 8 seconds? So what you do is you find the area under this curve, and we can find that by saying this is a rectangle. Well, I guess it's actually a square because it's 4 by 4. And so that's going to be a 16 area added with this triangle, which is going to be 4 times 4 divided by 2, which is 8. So 16 plus 8 is 24. So the total area under that acceleration curve is 24. So the velocity changed by 24. If the initial velocity was 0, then the final velocity would be that area. It would be 24. But since the initial velocity was not 0, it was 10, then we just add the 24 with the initial velocity of 10, so that the final velocity will be 34. All right, that's what this explanation says. You can read that more if you want to. And we're done. That is it. We're now on the summary slides. All right, feel free to pause and read these if you would like to. That's it.